Alright guys, so last time we discussed this example where we were trying to figure out the approximation for the square root of x. And specifically we wanted to find an approximation for the number 18. And what we determined is that by using Taylor polynomials of higher and higher degree, we get smaller and smaller absolute errors, right? And the idea here is that as we get more and more Taylor approximations, more and more terms in our Taylor approximation, we're going to get closer to the true answer of the square root of 18. So they provide good approximations for our functions near a point A, but how accurate are these approximations? To answer this, what we're going to do is we're going to define the remainder. So the remainder for a Taylor polynomial is as follows. We're going to let Pn be the Taylor polynomial for n of order n for the function f. The remainder, in using this approximation for f at the point x, is just the distance between f of x and Pn of x. So for the previous example, what that would be is that x, in this case, would be 18, because that's the point that we are trying to approximate. And then furthermore, f of x would be the square root of 18. And Pn of x would be that polynomial that we used. So it would be, the 4 plus 1 over 18 1 over 8 times 18 minus 16 minus 1 over 512 times 18 minus 16 squared, if we're doing the second degree Taylor approximation. So it's just the distance between our true answer and the polynomial approximation. The issue here, however, is that whenever this theory was developed back in the mid-1600s when calculus was being invented, we didn't have a way of directly calculating the square root of 18, right? We didn't have calculators back then. And so the question was, how good is this approximation really? Like, how do we know how good that approximation is? And there wasn't really a good way to tell using this definition of the remainder. But what I will show you in a second is that we can actually define the remainder in another way that allows us to determine how good our approximation is. So, yeah, as I say here, the remainder is just the distance between f of x and the nth Taylor polynomial. And we don't generally know the exact value of f of x, so it's worthwhile to come up with another way to write the remainder so we can estimate our remainder. And there's a nice theorem for it. Specifically, it is this one, Theorem 11.1. And here's the idea. We're going to let f have continuous derivatives up to n plus 1 on some open interval I containing a. Don't worry too much about the technicalities here. We'll never give you a problem that doesn't satisfy these conditions. So for all x in I, we define the function to be Pn of x plus Rn of x. This is basically just the same thing as on the last slide, except we added Pn of x to both sides. Where Pn is the nth degree Taylor polynomial for f centered at a, and the remainder is this thing. It is the n plus first derivative of f at c divided by n plus 1 factorial divided by x minus a to the n plus 1 power. So that looks like a mouthful. But the idea here is that the remainder, instead of writing it like this, where we don't know what f of x is, we can write it in this format, where c is some point between x and a. And so this replaces one difficulty with another. In the first definition of the remainder, we didn't know what f of x was. In this definition of the remainder, we don't know what c is. It's just some number between x and a. We can guarantee that there is some c between x and a for which the remainder is exactly this. Okay. And so this leads us to the nice conclusion that our function, f of x, is equal to its Taylor polynomial, its nth degree Taylor polynomial. This thing is Pn of x. And then we add on the remainder. This is our n of x. And so basically, what I am claiming to you is that if x was 18, and we were doing that square root function, we would be saying essentially that the square root of 18 is equal to 4 plus 1/8, 18 minus 16, minus 1 over 512 times 18 minus 16 squared, plus f to the n plus first power of c. So we would have to take the n plus first derivative. In this case, n would be 2, so we would be taking the third derivative of our function, evaluating that at c, dividing by 3 factorial, and multiplying by 18 minus 16 to the third power, where c is some number between, let me write this a little less notationally heavy, where c is between, that b/w means between 16 and 18. All right, and you could calculate the third derivative of our function. In fact, we have an example coming up where we will do that exactly. But yeah, this is the way that we write the remainder in this class. All right, so we have found an explicit formula for the remainder, but as I just mentioned, we generally don't know what c is equal to. But the theorem does say that c is between x and a, and so we can find an upper bound. So if we can find an upper bound on this thing, the absolute value of the n plus first derivative of f at c, for all c between a and x, then we can find a bound on the remainder. So remember that a is the value that is easy to compute, the center of the polynomial, and x is the value that we are estimating. So here is theorem 11.2, and here is the way that we estimate the remainder. And let me just say that this concept, arguably, is the hardest one that you will encounter through all of Calc 2. So if it doesn't make sense on your first listen through, that is okay. If it doesn't make sense on your second listen through, that is okay. This is a challenging concept that took me a while to understand whenever I was learning it for the first time. So don't get too frustrated if you don't quite get it yet. So let's read through this. We're going to let n be a fixed positive integer. We're going to suppose that there exists some number m. This is your upper bound. There exists some number m such that the absolute value of the n plus first derivative of f at c is less than or equal to capital M. So that's what it means to be an upper bound for all c between a and x inclusive. So the remainder in the nth order Taylor polynomial for f centered at a will satisfy this inequality. So the thing that is important for us to note is this piece and this piece. All right. And the idea is that m, once again, is your upper bound for, I'll write it one more time. For the absolute value of fn plus 1 evaluated at c, for all c between x and a. And we'll do an example of this in a minute, so hopefully that'll make it at least a little bit more clear. So the idea now is that instead of worrying about specifically what our c value is, we are just going to come up with an upper bound for this term. So we don't have to know specifically what our exact c value is. We just have to know an upper bound for our function. So let's give that a shot. So we're going to consider this example, once again, where we were trying to estimate the square root of 18 by using this polynomial. All right, so step one, we're just going to identify n, a, x, and f of x for this example. So n, in this case, is equal to 2 because we are using the second degree Taylor polynomial to estimate our function. A is the center of our series. It's the value for which we are estimating the square root of 18. In that case, it's 16. X is the value that we are estimating. It is 18. And f of x is the square root of x. All right. Now we are going to write down the general form for Rn of x. So Rn of x, by Theorem 11.1, is equal to the n plus first derivative of f evaluated at c divided by n plus 1 factorial times x minus a to the n plus 1 power, where c is between a and x. Okay. So this is the general form for Rn of x. Next, we are going to evaluate the absolute value of this f n plus 1 at c, and we are going to find the largest value that this can assume for c between a and x. So let me show you what I mean. So f n plus 1 c is equal to just the absolute value. In this case, we said that n was equal to 2, so we're just going to plug in a 2. We're taking the third derivative of our function and evaluating it at c. So, remember our function was the square root of x, so this was f of x. The first derivative, we calculated that to be 1 over 2 root x. The second derivative, we calculated that to be, let's see, this is negative 1/2 times x to the negative 3/2 times 1/2. Right? So this should be minus 1/4, I think. And the third derivative, if we take a derivative again, this is just going to be positive 3/8 x to the negative 5 over 2. So that's our third derivative. And so if we write that here, this is going to be the absolute value of 3 over 8x to the 5 over 2 power. Okay. And what we are going to say is that this thing must be less than or equal to m. M is going to be our upper bound for that entire thing. And this should not be an x in the bottom, I apologize. That should be a c right there because we are evaluating this as c. All right, so c in this case must be between 16 and 18. So c is between 16 and 18. The idea is that the largest value that 3 over 8 c to the 5 halves can take occurs when... So I want you to think about this for a second. If c is between 16 and 18, where it could be 16 or 18, endpoints are included, what is the largest value that this function occurs at? Will it occur at c equals 16? Will it occur at c equals 18? Or at some point in between? The idea is that this is actually maximized. The largest value that it can take on is maximized when c is equal to 16. And that is because c to the 5 halves, right there, that is a function that is increasing. And so if it is in the denominator, then the entire phrasing, that 3 over 8 c to the 5 halves, is a decreasing function. And since it is a decreasing function, it is maximized at the starting endpoint. Lots of things to think about, kind of confusing. So the idea here is that this whole thing, the absolute value of 3 over 8 c to the 5 halves, must be less than or equal to 3 over 8 times 16 to the 5 halves. And that is our m. This thing is the upper bound. And this is true for all c between 16 and 18. And if we simplify that, we could say that m is equal to 3 over 8192. So we have found an upper bound for the third derivative of our function evaluated at c. And so part D is to use this information to find a bound on Rn of 18. All right, so this we will have to use theorem 11.2 for. So using theorem 11.2, the absolute value of Rn of x is less than or equal to m times x minus a to the n plus 1 power divided by n plus 1 factorial. So for us, this means that R2 of x is less than or equal to 3 over 8192, because that's what m is, times 18 minus 16 to the third power over 3 factorial. And if we actually compute all of that, we get that R, and I made a small typo, this should not be R2 of x right there. That instead should be R2 of 18 because we plugged in x. So then R2 of 18, the remainder whenever we're evaluating 18, is less than or equal to 1 over 2048. So here's the conclusion statement. The idea is that the remainder in estimating square root of 18 with P2 of 18 is no larger than 1 over 2048. All right, and let's go back a few slides just to verify that this makes sense. Whenever we were doing this specific example with the second degree Taylor polynomial, we found that the error was 4.5 times 10 to the negative fourth. And that indeed is smaller than 1 over 2048. So the remainder, the actual remainder, we guaranteed was smaller than 2048. 1 over 2048. Okay. So let's continue with some examples. The hardest part of these problems is figuring out what m should be. For the following cases, we're going to try to determine m. Remember, m is the largest value that this derivative can take on for c between x and a. So suppose that my function is e to the x. Suppose that the x that I'm trying to approximate is 0.45. Suppose that a is equal to 0. That's kind of close to 0.45. And that n is equal to 100. So we have that f n plus 1 evaluated at c is equal to absolute value of the 101st derivative of f evaluated at c, and the 101st derivative of e to the x is just e to the x. If we plug in c, we get e to the c. Since e to the c is always a positive number, we can get rid of the absolute values and just write this as e to the c. All right. So let me write out a paragraph now. E to the c is an increasing function. Right? We all agree with that? As c increases, that function value increases. So where is that maximized? Whenever c has to be between 0 and 0.45. Well, it's maximized at 0.45. So e to the c is maximized at c equals 0.45. The issue, however, is that without a calculator, we don't know what e to the 0.45 is. And so it doesn't really make sense to use this as an upper bound. So let's just come up with another clever way to think about this. We know that e to the c must be less than e to the 0.45, but this, let's come up with a slightly worse upper bound, right? We just need to come up with some upper bound. So e to the 0.45 is less than e to the 0.5, right? And that is less than, or actually that is equal to the square root of e. And the square root of e, since e is about 2.7, this has to be less than 2. And the reason for it is because, actually an easier way to see this, let me break this into one more step. This is less than, why does it change colors? This is less than the square root of 4, because e is certainly less than 4, and so this is equal to 2. So what we're essentially saying is that e to the c is less than 2. So in this case, we can set m to be 2. This is an upper bound for this derivative, but we don't need it to be perfect. We don't need it to be the best upper bound. We just need it to be an upper bound. So we say m equals 2. Another upper bound that would work is 3, or 5, or 29, or 1,000,000. Those are all upper bounds. And you could show it with similar logic. But the idea is to come up with a pretty good upper bound, so that way we can get a good result whenever we are trying to compute our error. Okay, let's try another example. Suppose that we know that the fifth derivative of x is this negative 7 over x to the 1/3 power. Suppose that x is equal to 27.5, a is 27, and n is equal to 4. All right, so once again, we are trying to calculate the n plus first derivative of f at c. Well, they actually gave that to us because that is the fifth derivative of our function, which we are told is negative 7 over x to the 1/3 power. But since this is in an absolute value, we get rid of that minus sign. So this is just going to be written as 7 over absolute value of x, or sorry, we change to c. Absolute value of c to the 1/3 power. Okay. So this is a decreasing function on 0 to infinity. So let's think about that for a second. So the function c to the 1/3 is an increasing function. Since it's in the denominator, it is a decreasing function. All right, so 7 over absolute value of c to the 1/3 is then maximized, since it's a decreasing function, and c must be between x and a, it is maximized at the first value in our interval, which in this case is 27, is maximized at c equals 27. So 7 over c to the 1/3 is less than or equal to 7 over 27 to the 1/3. And of course, the cubed root of 27 is 3. And so this is 7 over 3. And this entire thing is our m. So 7/3 is an upper bound for this function where c must be restricted between 27.5 and 27. Okay, let's continue. Now we're going to find a bound for the magnitude of the remainder for the Taylor polynomials of f of x equals cosine of x, centered at 0 for any given n. So let's try and write some stuff down. Rn of x, in this case, let's just write down what our remainder is. It's always a good place to start. Is the n plus first derivative of f at c divided by n plus 1 factorial times x minus a to the n plus 1 power. A, in this case, is 0. So that's equal to 0. And so now let's try and compute the n plus first derivative of our function at c. So the problem is that whenever we start taking derivatives of cosine of x, it will cycle, right? It goes negative sine, negative cosine, positive sine, positive cosine, negative cosine, etc. And it cycles like that. And so if we're trying to find the n plus 1 derivative of this function, it's kind of challenging. And in fact, we don't know exactly what it should be. But we can write this. It's going to be plus or minus sine of c if n is even. Right? It'll either be positive sine of c if it's even. So that would mean that we take an odd derivative of our function. Or plus or minus cosine of c if n is odd. In any of these cases, no matter what it is, we have the following. The absolute value of f n plus 1 at c is less than or equal to 1. Right? Because no matter which case we fall into, sine and cosine are always bounded by 1, right? That's the largest they could ever be. So we can say that m is equal to 1. Now we can bound the remainder. Absolute value of Rn of x is less than or equal to the absolute value of f n plus 1 evaluated at c divided by n plus 1 factorial times x to the n plus 1 power. Remember, that should be x minus a, but a in this case is 0. All right, and the idea is that this is equal to the absolute value of f n plus 1 evaluated at c n plus 1 factorial times the absolute value of x to the n plus 1 power. And we know that this piece here is bounded above by m. Right, so this is essentially just using Theorem 11.2. So this is essentially Theorem 11.2. And so what we get is that this entire thing is less than or equal to 1 over n plus 1 factorial times the absolute value of x to the n plus 1 power. So the remainder, the difference between cosine of x and the nth degree Taylor polynomial that we approximate cosine of x with, is no bigger than this thing. And what you might notice here is that As x increases, so as x gets farther away from 0, our remainder will get larger. Like we can only guarantee that the remainder will be bounded by large numbers. And that makes sense because the estimate is better closer to 0. All right, let's continue. In section 11.2, we're going to see that the Taylor polynomial that approximates this function, centered at 0, is Pn of x equals negative x minus x squared over 2 minus x cubed over 3 minus blah, 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 all the way up to xn over n. So this is the Taylor polynomial that approximates the natural log of 1 minus x. So we're going to find a bound on the error in approximating ln of 1 minus x with p3 of x for values of x inside the interval negative 1/2 to positive 1/2. So now we're restricting x to be within a particular interval. All right, so let's do part A first, and then we will return and consider part B. So part A, I think this will have to bleed onto the next slide too. Yeah. First, we're going to write the remainder, Rn of x. In this case, n is equal to 3. And a, think about what a is for a second. A in this case is 0 because it is centered at 0. All right, so we have R3 of x. This is equal to the absolute value of f for c divided by 4 factorial times x to the 4th All right, and so what we must do is we have to find an upper bound for this piece. So this we are going to find an upper bound for. It is less than or equal to something. So let's try to do that. Let me use a different color. So I will just go ahead and tell you what the fourth derivative of this function is. We could start computing, f of x. I don't know why it's so thick. F of x is equal to the natural log of 1 minus x, and then f prime of x is equal to blah, 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 and then we could compute the fourth derivative. But in this case, I'll just go ahead and tell you that the fourth derivative of our function, evaluated at c, is equal to the absolute value of negative 6 over 1 minus c to the 4th power. All right, so what value of c, I want you guys to think about this carefully, what value of c maximizes this function where c is between a and x? So where c is between a and x is... All right, so c, so first of all, a we already decided was 0. But what is x? X in this case is just any number between negative 1/2 and positive 1/2. So now x can be variable as well. So x is somewhere within this range. So basically what we're saying is that c must be between 0 and x. So c also must be within this range. So what value for c between -1/2 and +1/2 allows us to conclude that this is maximized? This actually occurs at c equals 1/2. So think about it for a second. If we were to have plugged in -1/2 right there, we would get a larger number in the denominator. We would get 1 plus 1/2 to the 4th power, which is a larger denominator. The smallest denominator occurs when c is equal to 1/2. So if we then throw in 1/2, we can say, let me write it like this. This entire thing then must be less than or equal to 6 over 1/2 to the 4th power. And if we compute that out, this is 96. So our m is 96. So therefore, this entire thing up here, this f4 of c, is less than or equal to 96. Okay, so that's the first part. We have found a bound on our remainder. So continuing, we also have to ask ourselves, what value for x maximizes this function, x to the 4th? And that one's a little bit easier to see. Of course, that one is also 1/2. And 1/2 raised to the 4th power is equal to 1 over 16. All right, so if everything else has been confusing, here is the idea. The remainder, the absolute value of the remainder, Rn of x, I can guarantee to you that this is equal to f n plus 1 evaluated at c divided by n plus 1 factorial times the absolute value of x to the 4th power. This, by Theorem 11.1, I think 11.2 actually. This first one was Theorem 11.1. This is less than or equal to m times absolute value of x to the 4th power over 4 factorial. And this is less than or equal to 96, because that's what m was, times 1/16, because we can guarantee that the absolute value of x to the 4th is less than 1/16, divided by 4 factorial. And this number, whenever we compute it, is 0.25. Let me make one comment. This inequality is because absolute value of x to the 4th is less than or equal to 1/16. And so the conclusion statement is this: for all values x in the interval -1/2 to +1/2, the error in estimating the natural log of 1 minus x with p3 of x does not exceed 0.25. So no matter what x we choose between -1/2 and +1/2, the error in estimating this function with this polynomial never exceeds 0.25. The difference between those two functions is less than a quarter. Okay, so part B here asks us how many terms in the Taylor polynomial must we add to ensure that the error is no larger than 10 to the -3rd on the interval -1/2 to +1/2. So this one is a challenging problem. So let's go to the new slide. So let me rewrite the hint. So let me label this. This is part B. Okay, so this is the hint that was given. If we simplify this, we can get rid of that minus sign. In factorial is always positive. And so what we're left with is just in factorial divided by 1 minus c to the n plus 1 power. And in fact, since c must be between -1/2 and +1/2, the value in the denominator, we could get rid of the absolute value as well. So we can write this as n factorial divided by 1 minus c to the n plus 1 power. Okay, so let me give you some bullet points on what to do. We need to start by finding a c within -1/2 to +1/2 that maximizes this function up here, n factorial divided by 1 minus c to the n plus 1 power. And c equals 1/2 does that. Once again, for the same reason that the denominator would be larger if we had any other value for c. Then we need to find an x within -1/2 to +1/2 that maximizes x to the n plus 1 power. And once again, x equals 1/2 does that. Alright, so here's the claim. Remember the question. It says, how many terms in the Taylor polynomial must we add to ensure that the error is no larger than 10 to the -3rd? So we are trying to figure out an upper bound for our remainder, and then we will set that less than 10 to the -3rd and solve for n. So we will, I probably should have written this above, we will find upper bound for remainder. That should have an n in it. And then we will set that upper bound less than 10 to the negative third. So yeah, I probably should have written this above. This is the general strategy. And then solve for n. And the reason that we talked about these two bullet points was so that way we could find the upper bound for the remainder. So let me write the following. Rn of x for any n is equal to fn plus 1 c divided by n plus 1 factorial times x to the n plus 1 power. Remember that our center is 0, so instead of x minus a, it's just x. This is less than or equal to, in this case, fn plus 1 at c. Using this hint up here, we discovered that the value of c that maximizes that is c equals 1/2. All right, and so if we throw in 1/2 into that, we would get n factorial over 1 minus 1/2 to the n plus 1 power. So we get n factorial divided by 1/2 to the n plus 1 power. This entire thing is divided by n plus 1 factorial, and x to the n plus 1 power, the absolute value of x, is less this thing. Let me start using colors instead of just saying it. This is less than or equal to 1/2 to the n plus 1 power, and we also discovered that this thing was less than or equal to n factorial over 1/2 to the n plus 1. Okay, and so we multiply by 1/2 to the n plus 1 power. And what you might notice is that this and this cancel. It might be a little bit difficult to see that, but it is true. And then we have n factorial divided by n plus 1 factorial. Which hopefully you guys remember, this is equal to just 1 over n plus 1. And so now we will set this value. This is our upper bound. This is the upper bound for the remainder. Rn of x. And so now we are going to set 1 over n plus 1 less than or equal to 10 to the negative third and solve for n. Well, if we invert both sides, we get that n plus 1 must be greater than or equal to 10 to the third. And then if we subtract 1 from both sides, we get that n must be greater than or equal to 999. So the conclusion here is that we must add at least 999 terms through our Taylor polynomial in order to ensure that the error is no larger than 10 to the negative third. So we have to add a bunch of terms in order to ensure that's the case. All right. And so there was a lot that we covered in this section. Let me go over a brief summary of what we talked about. The polynomial that approximates a function f of x is called a Taylor polynomial. And it is equal to, let's write out specifically what it is equal to. It is equal to f of a plus f prime of a, not divided by anything, times x minus a plus f double prime of a over 2 factorial times x minus a squared all the way up to the nth term, which is the nth derivative of f at a divided by n factorial times x minus a, to the nth power. I know that looks weird. Let's see if we can rewrite that. Better. Okay. Taylor polynomials approximate functions well near our center. So they approximate the functions pretty well, near x equals a. The more terms that you add to a Taylor polynomial, the better the approximation will be. And a Taylor polynomial is not exactly equal to the function f of x. The difference is called the remainder and is equal to f n plus 1 evaluated at c divided by n plus 1 factorial times x minus a to the n plus 1 power, where c is between x and a. That is our definition for the remainder. And we normally cannot calculate the remainder exactly, so we find an upper bound for it, specifically m over n plus 1 factorial times x minus a to the n plus 1 power, where m is an upper bound for the absolute value of f n plus 1 evaluated at c. Okay, so that's the section summary. That's all for section 11.1. Once again, I argue that this is a very difficult section, so if you didn't get this at first, feel free to come visit me in my office hours, and I'm more than happy to come and try and help you. But yeah, this is a challenging section, or if you have questions, you can just leave them in the comments, and I'll try to answer them there. And yeah, make sure to just, do practice problems, read over the definitions, the theorems a few times to make sure you get it. And this is a super useful section whenever you get into later branches of mathematics and also into engineering. So it's good to have this sort of concept under your belt. All right, so with all that, I'll go ahead and stop here, and I will see you guys again in section 11.2.